In this video, we discuss the Fermat's little theorem. It states that if p is a prime number and it does not divide an integer a, then a to the p minus 1 is congruent to 1 mod p. To prove this theorem, it is useful for us to write n bar equals the remainder when n is divided by p. In other words, n bar is an integer which is greater than or equal to 0 and less than p, such that n is congruent to n bar mod p. Now, let's consider the sets S, which consists of numbers 1, 2, 3 up to p minus 1, and SA, which is the set containing a bar, 2a bar, 3a bar, up to p minus 1 times a bar. Note that by definition, SA is contained in S. Now, suppose that k1 and k2 are integers such that 0 is less than k1, is less than k2, is less than or equal to p minus 1. Then, 0 is less than k2 minus k1, which is less than p minus 1. This implies that p does not divide k2 minus k1, which in turn implies that p does not divide k2 minus k1 times a, because otherwise p divides k2 minus k1 times a, which would mean that p has to divide k2 minus k1 or p divides a, and both cases lead to a contradiction. So, k1 times a is not congruent to k2 times a mod p. This means that the set SA has distinct elements. Since the size of SA equals p minus 1, which is equal to the size of S, and also SA is contained in S, we have that SA is equal to S. Now, the product of the elements of SA and S are equal. In other words, 1 times 2 times 3 times all the way to p minus 1 is equal to a bar times 2a bar times 3a bar times all the way to p minus 1 times a bar. The left-hand side is just p minus 1 factorial, which is congruent to a times 2a times 3a times all the way to p minus 1a mod p. We can rewrite the right-hand side by multiplying the coefficients of a first, which is p minus 1 factorial, and then multiply all the a's, and since there are p minus 1 of them, we have a to the p minus 1. Finally, we check that the HCF of p minus 1 factorial and p equals 1, so we may divide both sides of the congruence by p minus 1 factorial to get a to the p minus 1 is congruent to 1 mod p, where we have applied a result from the fourth number theory video. So we have completed the proof. Fermat's little theorem allows us to reduce some congruences faster than we can before. Let's consider this example where we want to reduce 5 to the 23 mod 11. We have seen how we can do this by successive squaring in the last video, but here we can do it much faster. We check that 11 is prime, and it does not divide 5, so using the Fermat's little theorem, we have 5 to the 10 is congruent to 1 mod 11. To make use of this result, we use the division algorithm to write the power 23 as 2 times 10 plus 3. Now, 5 to the 23 can be written as 5 to the 2 times 10 plus 3, which is 5 to the 10 squared times 5 to the 3, which is congruent to 1 squared times 125. We can easily reduce this to 4 mod 11, which is the same answer as we get before. Notice, we only need to compute 5 cubed instead of 5 to the 16 required in the method of successive squaring. More specifically, successive squaring is impractical for reducing a to the k mod p when k is large. However, using the Fermat's little theorem and the division algorithm, every power of a to the p minus 1 goes to 1, so the largest power that we need to compute is at most p minus 2. Let's look at one more example. we want to reduce 67 to the 598 mod 41. If we use successive squaring, then we need to find the power of 67, which is the largest power of 2 less than 598, which is 512. So we have to compute 67 to the 512, which is doable but time-consuming. So again, we try to use Fermat's little theorem. And we can do so because 41 is prime, and 41 does not divide 67. So by Fermat's little theorem, 67 to the 40 is congruent to 1 mod 41. Now, we use division algorithm to write 598 equals 14 times 40 plus 38. So we need to compute 67 to the 38, which is a lot easier than 67 to the 512. However, bear in mind that this only works if the modulo p is prime and does not divide the base number a.